Hi everybody, here we are with our next set of videos from section 3.7, and I'm noticing already that the clarity here much crisper than when I was filming from my office. So I'll just show you guys really quick. I'm going to be doing this from my front porch. Yeah, here I am. So I've set up a makeshift office here. I've got my table, the computer, notes, books. There's my son's stroller. Got all there's our textbook there. We got a freezer stocked full of goodies. So I'm all set here. There's kind of got this nice shade here, but yeah, you can see my neighborhood. Okay, anyway, next section, 3.7. Hope you guys are doing well, and the recent announcement from the governor of California came out, I think yesterday or something, not to go out at all unless you absolutely have to buy groceries and things. So we're all pretty loosely quarantined. What do we have today? Elasticity of demand. It's kind of a fun section to wrap up this chapter. It's another application. I would have to believe for most folks not nearly as demanding as related rates. Related rates, some problems are fine, other ones can really be a challenge. Elasticity of demand, though, pretty cool. So we're going to think of, like, the question is, what is the relative rate of change that you see there at the top? And so we'll think, okay, a relative rate of how much is something changing relative to how much of it there is in the first place, right? So what's the rate of change divided by the original value, right? So a rate of change, of course, is a derivative, maybe f prime of x. The original value is just the original function. To kind of make some sense of this, we'll see some applications toward the end of this section. But to make some sense of it, think, hey, the rate of change, and I just think of the virus, right? So what if there were 10 new cases per day of people catching the coronavirus? 10 new cases per day. You think, well, like, who are you talking about? So 10 new cases per day for the entire world? Are we talking about the entire world? Well, that's tiny. That's minuscule. That's virtually nothing. 10 new cases. But what if it was 10 new cases for the students at Miramar? Like, well, 10 new cases per day, and we're just talking about Miramar. Maybe that's actually quite a bit. It's definitely quite a bit more relative than to the world, right? Okay, so we've got a nice formula for it. The derivative divided by the original function. There you go. Hand in hand, before we get to an example, we'll think, what is the percent rate of change? Just give me one. Okay. What's the percent? Okay, well, take the relative rate of change. That will be some kind of a decimal value. If we multiply it by 100, we can turn it into a percent. Okay, makes sense. So we're going to start off with this one. We're given a function. Find the relative rate and the percent rate of change for f of x equals 60x minus 1.2x squared. And we're going to do this for the x value 5. More context to come later. We're just dealing with the function and some numbers. I think that's a good place to start. Okay, well, if you remember our formula, the derivative divided by the original, we're of course going to need the derivative here. So our derivative, f prime of x equals 60 minus 2.4x. And so we'll think, okay, if we take the ratio to get the relative, we'll take the derivative divided by the original. Of course, we want to plug in 5. So we'll plug 5 into the derivative, we'll plug 5 into the original, divide them, and there you go. In this case, and we're going to round these, it's going to be the same in your homework, the relative here, 0.178. We asked for the percent rate of change as well. And okay, well, multiply that by 100, 0.178 times 100 to get your percent rate of change, 17.8% in this case. Okay, moving on. Let's try another one. Of course, we might see anything here that we're able to take a derivative of. We can take derivatives of just about anything. So maybe here f of x equals 9x minus 5 natural log x at x equals 3. So we can think, hey, what's the derivative this time? F prime of x, in this case, is 9 minus 5 times 1 over x. So hopefully these are getting more and more familiar, getting really comfortable with taking these kinds of derivatives. So, okay. Oh, let's clean that up a little bit. Maybe just 9 minus 5 over x. And we take the ratio, the derivative divided by the original. And we'll plug in 3. And I think I'm just giving you everything right here. Try and pull that to the center a little bit. Plugging in 3 to all our x values. Hopefully you can get that same relative rate of change that I got, 0.341. Convert that to a percent to get the percent rate of change, 34.1%. And there you have it. One note I want to make just before we conclude this first video. You may or may not have realized that formula, this whole time, f prime of x divided by f of x, was actually the derivative for the natural log of f of x. Right? Think about the chain rule. There's an outside and an inside derivative of natural log. We do 1 over f of x, but then we multiply it by the derivative of our inside. And okay, sometimes, and this is really just for your future reference, maybe you take a class sometime in the future, maybe Math 122, maybe some economics course, and they start referring to the logarithmic derivative. They mean the relative rate of change. So you might see that in our book. I'm not going to use that kind of language. I'm just going to say find the relative rate of change. But just want to point out that if you do see that, that's what they mean. Okay, next up, I think we're going to stop here, but just to give you a preview. Next up, we are going to define, finally, elasticity of demand. So I'm going to pause here. Catch you guys in the next video.